We're about good to start. So you all got an introduction of me. My name is Anders Gannon. I'm a professor in the political science department, which is strange, here at Vanderbilt University, and I'm also a faculty affiliate with the Data Science Institute. So in my world of political science, we have a lot of the same data problems as folks in the neuroscience world. And we start all of this with, we should all largely be familiar with Maslow's hierarchy of needs. At the bottom, you have your basic needs that you need, like food, shelter, clothing, water, all the way to the top for self-actualization. And data has an exact same hierarchy. Where at the top is what we're all hoping to aspire to get prescriptive, causal understandings about if X happens, that causes Y. But before we get to the top, we have to go one layer down below that, which is understanding predictive data analysis. If we see X, do we tend to see Y? Whether or not there's something that's causing the relationship between those two things to happen. But before we even get that, we have to do descriptive data analysis. What is X? What is Y? How are these things happening? How are these things distributed? Where do we find them? What is the shape of these things out in the wild? And so that's the purpose of today's talk, is starting with the very bottom of this pyramid, those most basic and foundational needs, to understand if we look at data and we see what exists in that data, how is that a starting point for seeing how patterns might emerge so we can get to the top of this pyramid and understanding true causal relationships of things that we're interested in. So that's the purpose of exploratory data analysis, or what I call EDA. The first is to communicate. You're presenting data and you're just saying, here's what we know about some data that has information about things in the past. How can we present that data to explain and inform with evidence? And second is to analyze, to give us a starting point of building the foundation of that pyramid so that we know here's patterns that might start to emerge, here's things that the data might be able to tell us, and here's also limitations to that data. So we do this with descriptive statistics, with basic math that some of us, not me, learned in high school, but that we all are starting to get an idea of, to understand what are the values that exist in our data, what outliers are there, where there's some extreme weird cases that might just be weird, but might also indicate a problem with the data, and what's the distribution of the data to help us know what types of statistical techniques we'll use later on. So there's two basic principles that we use in exploratory data analysis. And these seem to contradict, but they actually make a lot of sense and they tie together really nicely. The first is you can always present something simpler. Always. If you have data that exists to create an image in 3 dimensions, try to make it 2-dimensional. If you have 10,000 observation points, try to show 1,000. And so always make something simple. And once you've done that, you can now do the opposite. You look one level below an existing description. So add a single layer. You've shown 2 dimensions, now add the third. You've shown 1,000 observations, now show 2,000. So you start by simplifying and then you add additional layers on to see how much we need. So we're always going to be happy when we simplified something, and then we always are going to be able to describe then one layer deeper at a time. So exploratory data analysis fits into this pipeline. That's how I think all data problems should be approached. You import your data, get it from outer space where it exists onto your actual computer. You tidy the data to organize it in a way that you need. Then you engage in this cycle of transforming the data by adding new variables, adding new rows, changing the names of things, visualizing how those changes are happening, and engaging in some statistical or mathematical modeling. And then lastly, you communicate. Here's now what we know about the data by just looking at it and describing it. But in reality, this is a lot messier. There is no nice start at point A and end at point Z. These things all interrelate with one another, and you're constantly doing all of these processes simultaneously. So if it feels like you're trying to build a foundation of the house at the same time that you're creating the plumbing, at the same time that you're putting in the electricity and the HVAC, and one of these has to happen first and second, but they all kind of have to happen at the same time, that's correct. That's the point. And so we do that and we engage in this process iteratively over and over, building all parts of this data science pipeline house at the same time to organize the data, to spot problems in the data, and to identify ways that we'll model the data once we know what it looks like. So ways that we would describe a data set. So we start with key descriptive statistics. What I'm showing here is code that's from Python that reads in a data set that has some information about COVID cases. And so we start always with something really simple, which in this case is a single line of code in Python that just says, describe this. That's it. Just describe. And now we can see different columns of the data and some descriptions about those columns. What is the count? How many values do we have in that column? What's the mean value and the standard deviation to give us some sense of central tendency? What's the minimum value? What's the 25th percentile, the 50th, the 75th, and the maximum? If we take a second and look at this, I'll just sort of give you the preview that this is data about COVID cases that exist in different cities in Italy. We can start to see things that look weird. There was negative 148 COVID cases in some city in Italy. That seems really low, too low, roughly 148 lower than you expect to be possible for a number of COVID cases. So already, by just saying, give me basic statistics about the data, we start to see maybe there's some problems here. Maybe someone had a typo when they entered the data. Maybe there was something weird in how this got from paper into a computer. Maybe there's something weird with Python in my Excel file. So already we're finding out things about our data. We're doing the most basic, simple explorations about what the data looks like. So there's some things that we can interpret beyond just, is there something that's wrong because we have a negative value where we shouldn't, by looking at these key descriptive statistics. When we have a low variance in these numbers, we know that we have values that are really close to the mean. So if we look, what we're seeing here is for the variables that are numeric, show me what the variance is. And so the lower these numbers are, the closer those values are to their mean. So that tells us that the number of new tests in each city was pretty similar from city to city and from month to month. But the number of new deaths varied a lot. In some places, there was a high number of deaths. Other times, there was a low number of deaths. So it tells us that there's these peaks and valleys, these spikes, and how that variable is changing over the course of our data. We can do the same thing with the skewness of the data, which shows us how symmetrical it is. Do we have some very small values and some very large values? Or do we have a lot of very small values and some very large values? And so that skewness tells us whether we have outliers that exist of some really, really big numbers and some really, really small numbers. And so that already tells us something useful as well. Descriptive statistics, though, can be really misleading. There's only so much that you can tell by knowing things like these averages. What I have here are information about 4 different data sets that all have the same count. Okay, the same number of rows. That's good. The mean looks about the same. The standard deviation looks about the same. The count is the same for this other y value, and so is the mean and standard deviation. So here's 4 different data sets where it looks like these variables are the same thing in terms of aggregating those summary statistics. But if we look at them, they're all incredibly different. These are those 4 data sets. All 4 of these plots have the same mean and the same standard deviation for x and y. And they're super, super different from one another. Some of these might be how I want to think about something like COVID cases, and others look really weird and fake and look like a made-up dinosaur, which is very impressive, but maybe not useful in the data world. So what we take away from this is always look at your data. The descriptive statistics are great. They're super useful to know things like the mean and the maximum and the minimum, but always look at the raw data and you'll start to see patterns, maybe images, maybe animals that begin to emerge from those things. So I start from the perspective that if someone else made data, do not trust it. If your own research assistants made the data, do not trust it. If you yourself made the data, do not trust it. Because there's way too many cases of data that people assume works and is good, but that has problems that we find out later on with really, really important consequences. And there's 3 that I'm going to highlight here that are ones that have kept me up at night and that hopefully cause you to think the same with data in the future. The first is that Microsoft Excel has a limit on how many rows it can have in its data. It's something in the millions. So there's a lot of rows that you can have, but there's a limit. Now, there was a county in New York that was counting the number of people that have gotten COVID tests, and they entered all of this data into Microsoft Excel. And then they clicked save. And when they clicked save, Microsoft Excel said, everything after row 2 million, I can't. It's too much for me. And it just disappeared. So we had an incorrect number of COVID cases that was caused just by the limit on how many rows Microsoft Excel can operate. Those of you that use Excel also know that it will change the names of things for you. It tries to guess if you type 10/1, oh, that means October 1st. That's reasonable in a lot of cases, but turns out that there's a bunch of genes that have names that seem really similar to months, that start with OCT or that start with DEC. And so anytime that these scientists were entering data about these genomes into Excel, it was automatically changing those things to a date. And once people figured this out, they estimated that 25% of published papers in genomics had errors in it because they used Microsoft Excel, which automatically changed these genes into dates. The New York Civil Liberties Union also had a problem happening with this when it came to arrests for marijuana usage, where what they had is they had one data about demographic data of how many people of different races, ethnicities, and genders lived in different cities. They had a different data set that was information about people that had been arrested. They merged those two things together, and they found that there was a certain set of neighborhoods of predominantly minorities where there was almost no arrests for marijuana. They thought, wow, this is really strange. Maybe this is overturning what we think about racial bias that exists in policing. Turns out that's not the case. It's just that one of the data sets listed the city as St. Lawrence. The other listed it as St. Lawrence. So when you merge those two things together, you and I can tell that St. Lawrence and St. Lawrence are the same city, but the computer cannot. And so it just dropped all of those cases and said there's no instances of arrests happening in St. Lawrence because all these arrests happened in St. Lawrence. So these are really simple problems. These are problems that can easily be resolved and overcome by looking at the data, by describing it, by saying, should we see a bunch of these cases drop out in certain cities? So why do we have missingness that exists in the data? Well, sometimes it's because people opt out. All of us have filled in surveys provided by our universities, our employers, or Yelp reviews. And I only leave a Yelp review if it's the best meal I've ever had in my life or the worst meal I've ever had in my life, but nothing in the middle. So when I think about decisions made by subjects who are the ones whose data is being collected, there's also errors that happen in record creation, how things are entered, what software is used, and examples that I described, coding errors if somebody's entering the data by hand. We want to think about what we do. And there's no universal solution to this, but I want to really quickly give you 3 solutions that I think are okay. What we see here is a comment that says, use the CRS database to size the market. That data is wrong. Use the SIBS database. That data is also wrong. Can you average them? I can multiply them too. So there's a lot of wrong ways to approach data and exploratory data analysis. Here's some ways that I think get us kind of close. When we're deciding what to do computationally, we want to figure out how much data is missing. Is this data missing in the response variable that we're interested in, the thing that we're maybe trying to predict or explain, or some predictor variables? What type of variable do we have the data missing in, quantitative numeric ones or categorical ones? Should NAs be allowed? How do we think about outliers? And how do we merge things like St. Lawrence and St. Lawrence to get multiple data sets to exist together? So the first thing we can do is impute those missing values with the mean. So we see here is a data set that's about people that died on the Titanic. And there's some columns where there's information that's missing. What we see here is that the survived column only has 891 values, even though there's 1,309 rows in the data set. So there's some people that we don't know, yes or no, did they survive on the Titanic? So the first thing we can do is just impute the mean for these variables, or in this case, we're doing it for something like age, that says, what was the average age? Okay, so now if any row is missing the value in the age column, impute that mean. So some benefits that this has is the mean is the average, and so we're not changing the average by filling in that value there. But that also might not be necessarily where those values are missing. So we can make the standard deviation too small by imputing the mean value. But that is one option. A second option is to take a random sample. Anytime some value is missing, take a random value that exists and throw it in there. So we're not imputing it with the mean. What we're doing here is we're dropping those NAs and replacing it with the sample. So we're saying in that column called age, anything that's an NA, replace it with a random value that exists. So here's someone's age in row 400 and throw it in there for the missing value in row number 4. So that's an option. We can also do something more complicated, like what's called k nearest neighbor. which is find the row that's most similar to this row, figure out what is their value that's missing, and then impute it in there. So let's say that we had my transcript for my grades at Vanderbilt. We don't know what grade I got in data science 3100. For some reason, that's missing. We find another student whose transcript is most similar to mine. We got the same grades in the same other classes. And then we can maybe infer that their grade in data science 3100 is the most similar to mine. So we can impute that value or put in that value there. And so here we're using a k-nearest neighbor imputer. We're saying take the two other students who are most similar to me and put their value or the average of their values in for the one that's missing for me. So these things are all a start. I don't imagine that I've resolved your concerns about data that's missing in marijuana usage or in COVID cases or anything like that, but we can start to see ways in which looking at the data, identifying flaws that exist in the data or strange outliers can give us a sense about what this looks like. And the thing that's sort of paradoxical to people is that this is most of the job. Despite me being a faculty that's doing data science, 90% of my job is seeing data that's ugly, messy, and incorrect and fixing it. 9% of the job is taking existing off-the-shelf tools that people have been using for decades, giving it some fancy new name like machine learning when it's just statistics. And 1% of that is the new cutting edge models that were just created. That's ChatGPT number 6.0, which probably came out 10 minutes ago. I'm not sure. But that's the foundation of everything else. We're starting at the bottom and the base of that pyramid. This is an image of a dog that's made by Pablo Picasso. And it's widely regarded as one of the best images ever created by an artist of a dog. And it was one of his friend's dogs that he's hidden or inserted in a bunch of his paintings. Now, there's something really beautiful about this dog. It's incredibly simple. I think my 9-year-old nephew could draw something like this as well, but it's instantly recognizable, despite being done without even having to lift a pen. This is a single stroke of a pen that creates an image of a dog that we know. And that's how we want to think about how we analyze and approach data, is start with the simplest. Start with the base of that pyramid, doing explorations that identify the mean, that figure out the maximum, the minimum, that look at weird outlier values, and that do simple plots to see, does my data look like a dinosaur, an X, or a bullseye? And once you know those things, now you can start adding fur to this dog and eyeballs. You figure out what color and what type of dog it is. And that's how we move beyond while still recognizing the beauty and the simplicity of the image. So I've got about 10-ish minutes now for questions. Thank you all for your time.
I've spent a lot of time thinking about some data, and I think it's really great that you did this. Thank you. I wanted to get your thoughts on, there have been a couple R packages that I've been messing around with recently, not like to do anything, but just to learn. So if you're like, I'm going to use your garbage, it's totally fine. They were like, in R, like the mice algorithm, and then there's like a Miss Forest, and then you can put them together and make a Miss Ranger. Do you know what I'm talking about?
Yes, I do.
Okay, great. That's awesome. Can you talk about your thoughts on those things for a few minutes?
Sure. Yeah, so the packages that are being mentioned here are sort of ways that are similar to that k-nearest neighbor algorithm I talked about that are algorithmic ways of replacing missing data. The basic logic that exists here is create a new column in your data that is the value missing? And you say yes or no. So you have a binary value in that column. Now what you do is you're building a predictive model that says what explains whether or not a value is missing. And so what these models do is they take all of your other variables and they try to say people with a certain value in some set of columns are more or less likely to have a missing value. So let's go back to that Titanic example that we had, where we're missing the age that exists for a bunch of passengers. What we can do is create a new column that says, is the age column missing? Yes or no? And what other variables help us predict whether or not the age column is missing? So now we can see, oh, the lower class someone was on the ship, the more likely it is that they're missing a value for age. If someone is a woman as opposed to a man, it's more likely that we're missing the value for their age column. Maybe they weren't the one who bought the ticket or they didn't record the information. And so now if we know those things that help us predict the missing value that exists there, then that allows us to maybe make some inferences about how we fill those things in. Now, the way that the models that you described do that is by taking columns or taking rows where we do know the value for something like their age, pretend we don't know it, and see how well we can predict what the correct value is. So what we see these models doing is they separate the sample into a training and a test set, and then they try to say, okay, let's predict in row number 6, what would be the value for their age if I didn't know it and I hadn't seen it. And then it runs that model iteratively over and over and over again. That's especially what the random forest model is doing. It's running this over a bunch of different cases and saying, okay, here's now the model that best predicts the age and the one where we know the true answer, but we pretended that we didn't. And then we apply that model to the cases where we don't know the true answer. And we just kind of cross our fingers and hope that there's enough similarity in those two things, but we're recognizing limitations in our ability to verify or validate. Does that help answer the question? Great.
Do you have any like preferences? Like, I know your answer probably depends, but like, do you have any preferences?
I think mean imputation has a lot of problems. I think that artificially constrains the standard deviations in ways that are bad. And there's not a reason to assume that the values that are missing are similar to the values that we have. We know, for example, now after the fact in the Titanic data, it was all the children. If you were 3 years or younger, there wasn't information about your age in the ship's records. So we didn't know that. So even though the average person age on the Titanic was, let's say, maybe 40, none of the people that were missing were over 3. And so you can't assume that the data that's missing is same as the data that you have. K nearest neighbor, I think, is okay and does pretty well. What's important there is that you've standardized and scaled all of your other variables to be comparable. So if I have, for example, let's say there's health data and we're missing someone's glucose results for some reason, there's values that are missing in that column. One thing that we can do is say, okay, maybe the age, weight, etc. help. But age, weight, height are all on different scales. Some go into the hundreds, some isn't measured in meters or things like that. And so we have to standardize those things to be on a -1 to 1 scale or a mean 0, a standard deviation 1 scale in ways that then allow us to say, here's the 2 people that are most similar. So, because if I weigh 3 pounds more than someone, but I'm 3 inches taller than them, that's a pretty big height difference, but it's not that big of a weight difference. And so the model will not weight those things correctly if you haven't accounted for standardizing those things. And so that can be really tricky when you have categorical variables that you're then just turning into 0 or 1 columns. And so there's just a lot more pre-processing you have to use the data to do correctly. And I've often seen a lot of cases of people skipping those steps. So I think the more advanced models, like the ones that you mentioned, the random forest ranger, et cetera, and things like K nearest neighbor, require you to clean the data a lot and standardize it to be able to do those models. And then I think they work really well. But that step, again, is going to be 90% of the process. Yep.
I have a question. In this scenario where I work with like open data sets, so there's like missing data, like certain behavioral measures.
Yeah.
So like you're interested in both behavioral measures, but let's say one had like 150 and the other one had like 111. And I have my data for like all of them, but I have 115. But I want to look at the analysis between both. So is it, and then I can compare both of them. Does that make sense?
Yes.
Should I like just use the 111 because I have all the data for all of them, or should I? Is it okay for me to do like 150 for this analysis, looking at the behavioral data, and the other one just do the 111 because I'm using the maximum data for both? Right. But is there like, what's your opinions on like comparing that comparison? Like what's his? Yeah. I've seen that happen a lot. I've always wondered, like, what's like the best thing to do?
Yeah, it's tricky. And the unsatisfying answer I'm going to give is that whatever you do is going to be a little bit wrong. And so you just have to have some recognize that, and in your analysis and your results and your interpretation have caveats about that. And so what I recommend doing is kind of doing multiple extremes to give you some sense of the upper and lower bounds that exist for that. So try just deleting every row that has missing data and only work with the complete data and do your models. Now do the model where you keep the missingness in and you run whatever other analysis you do and you get results. And now try some imputation method, like nearest neighbor, something like that, and get results. You say, okay, here's 3 different sets of results. They're not identical, but they all seem to be between 10 and 12. And so we can think that we have some confidence that the results are somewhere in there. And so there's some applications where that's more or less satisfying or helpful. And you might get a result that indicates, hey, if we ignore the missing data, this is a really good drug to give someone. But if we impute the missing data, it turns out this drug doesn't work. And now it's really hard to know what to do. And so now what you do is you ask your funders for more money so you can do the experiment again. Yeah.
You can just talk, maybe a loaded question, but doing the exploratory data analysis on things in really high dimensional space, sometimes, I mean, you talk about visualizing the data, creating like intuitive visualizations for this, it kind of requires dimension reduction, and then you have to interpret like these strange latent spaces and things like that. So I guess, I know modeling, we can sort of make our predictors more sparse and you know, narrow things down, but how on the exploratory side, like what are some techniques that you use when you're kind of sifting through really dense, large data in high dimensions?
Yeah, so I'll always try to look and pick out specific cases in a set of 5. I'll always try and take the minimum, the maximum, the mean, and 2 random. And so like my data is a lot about military capabilities that countries have. And so I'm looking at for a country in a year, how many of every weapon do this country have? So I have tons of columns that exist in this data. So I'll just pick the smallest country, the biggest country, the most average country, and 2 random countries. And I'll sit and I'll just look. And I'll look at those 5 cases and what the values are across each of the columns and try to interpret and get a sense about what it looks like. And that generally gives me a reasonable sense of the overall span without having to worry about how do I visualize a bar graph that has 80 bars on it. There's not a lot that I can do with that information, but by just looking at the raw data on a pseudo-random sample, that starts to give me a sense about what the values and the general spans are. So doing that in combination with just get a table of those average values for these things can start to give me some sense. And also what I mentioned in the other answer is the like scaling and standardizing the values as ways to make things that are really big and weird and on different scales somewhat comparable to one another in ways that I can see what those general tendencies tend to look like.
And is there any like ethical, I guess, concern with like if you're working with healthcare data and you're trying to do some kind of missing data imputation? Thinking from like the perspective, we have longitudinal data set over 11 years, all kinds of health demographics, like blood draws, case happenings, those kinds of things. If there's pieces missing across the years, even if you have maybe some pieces 2 years before, 2 years after, what's kind of like the drawback, I guess, in terms of doing an imputation there and then doing an analysis, and then how do you justify, like, in a sense, like you were mathematically creating this data versus like just pulling it up and done thing? And like, how would you do that? And like, I guess, do you have any suggestions on like how to best approach that?
Yeah, the main suggestion I would do is just be very upfront and transparent about did you do imputation? And if so, how? And what would have happened if you didn't? And so place where I see this longitudinally is, you know, in January, here's the glucose level, and then here it is in December. We don't know it in July. We'll just put it smack in the middle. It's okay. That's the most common method that I see, but it has drawbacks of things like assumptions that you're making about when people got tests, things like that. So what I see that I don't like is hidden away in Appendix 4 on page 65 is a footnote that says, we did mean imputation for the longitudinal data to assume no change in the trend, when I think that should be in page 4 of the actual methods in the paper itself, where you say, I did this particular imputation method. Here's why I chose to do it. I've done additional models that show how the results would be different if I hadn't done that imputation at all. I had assumed we just don't know the data that exists there. So that's why I'm a big fan of just identifying how dependent are your results on the imputation that you did. And if it seems like you're getting similar results no matter what, then I think that you might be in okay shape. But I think also making clear in the data, here's the values that I imputed versus here's the true values are ways to deal with some of those ethical concerns. So say, here's a glucose test reading from June, but to be clear, that's fake. I made that up. I have reason to believe it might be roughly this value, but there's no test result that happened that gives that. And so keeping in the data some indication of here's the fake values that I put in are things that will help future researchers know things about the sort of ethics and privacy of things that we actually know about these patients and things that we don't. think we're about out of time, but thank you all so much for your time. Glad that you all are here doing this great initiative, and thanks to Lily and the folks here that invited me to come and give this talk. I very much enjoyed being here. Thank you all very much.